In this work, we propose a novel normal estimation method called SHS-Net, which can accurately predict oriented normals from point clouds with noise, density variations, and various structures. As an important geometric property of point clouds, normals with consistent orientation, i.e., oriented normals, clearly reveal the geometric structures and make significant contributions in downstream applications. Generally, the estimation of oriented normals requires a two-stage paradigm. 1. The unoriented normal estimation from the local neighbors of the query point. 2. The normal orientation to make the normal directions to be globally consistent, example, facing outward of the surface. In this work, we propose SHS-Net to estimate oriented normals directly from point clouds. Part 1. Method. Our approach includes two branches. We use a local patch PQ to capture the local geometry for accurately describing the surface pattern around a query point Q. Since the interior/exterior of a surface cannot be determined reliably from a local patch, we take a global subsample set PQ from the raw point cloud to provide additional information to estimate the sign at point Q. Thus, the signed hypersurface function at point Q is formulated as the product of the above two terms. We adopt a similar network architecture for patch and shape feature encoder to get the local and global latent code, respectively. The latent code Z is extracted through a series of MLPs and feature extraction layers F. Moreover, we design an attention-weighted normal prediction module to solve the unoriented normal and its sign of the query point from the learned signed hypersurface. Our loss function includes 4 items. The first item is the sin loss between the predicted unoriented normal and the ground truth normal at the query point. The second item is the weighted mean square error, MSE, of the oriented normals of the neighborhood points. For the normal orientation, we adopt the binary cross entropy H to calculate a sign classification loss at the query point. Moreover, we add a loss term according to coplanarity to facilitate the learning of weight, tau. Part 2. Experiments. Due to the lack of relevant datasets and the relatively simple test shapes of the PCP-Net dataset, we further collect shapes with complex structures from other public datasets, such as the famous dataset and the Stanford 3D scanning repository. We follow the same pre-processing steps as the PCP-Net dataset to conduct data augmentation, example, adding Gaussian noise with different levels, 0.12%, 0.6% and 1.2%, and uneven sampling, stripe and gradient. The ground truth-oriented normals are extracted from mesh data and used for evaluation. We call this dataset Famous Shape and it is publicly available. We report quantitative comparison results of oriented normals on datasets PCP-Net and Famous Shape. Our method achieves the best performance under almost all metrics and has the best average result. Additionally, we show the curve of percentage of good points, PGP, whose normal errors are less than the given angle thresholds. Our method has the best value for all thresholds. Meanwhile, we report quantitative comparison results of unoriented normals on datasets PCP-Net and Famous Shape. Our method achieves the best performance under most metrics and has the best average result. Moreover, our method maintains an advantage about PGP at the vast majority of thresholds. In the top figure, we show a visual comparison of the normal errors. The angle error is mapped to a heat map ranging from 0 degree to 180 degree. The purple indicates the same direction as the ground truth, while the red indicates the opposite. To verify the generalization ability of our method on LiDAR point clouds of outdoor scenes, we test directly on the KITTI dataset with the model trained on the PCP-Net dataset. As can be seen in the bottom figure, compared to the baselines, our estimated normals can facilitate the surface reconstruction algorithm to reconstruct surfaces that more accurately depict the spatial structure and distribution of real scenes. We also conduct extensive ablation studies to verify the effectiveness of the proposed modules and parameter settings. The ablation experiments include A. The feature encoding modules and the weight, B. The attention-weighted normal prediction module, C. Sin loss and sign loss, D. The point sampling strategies and other hyperparameters. Part 3. Demo and application. Here, we show the normal estimation results, oriented normal RMSE and surface reconstruction results from the column shape of different methods. Here, we show the normal estimation results, oriented normal RMSE and surface reconstruction results from the star-sharp shape of different methods. For more applications, we adopt a point cloud denoising algorithm with default parameters to filter the input noisy point cloud based on the normals estimated by our method. We use the Poisson surface reconstruction algorithm to generate surfaces from LiDAR point clouds using oriented normals estimated by different methods. In summary, our contributions include: we introduce a new technique to represent point cloud geometric properties as signed hypersurfaces in a high-dimensional feature space. We show that the signed hypersurfaces can be used to estimate normals with consistent orientations directly from point clouds, rather than through a two-stage paradigm. We experimentally demonstrate that our method is able to estimate normals with high accuracy and achieves the state-of-the-art results in both unoriented and oriented normal estimation. Our paper, dataset and source code are publicly available online. Thanks for your attention.